Welcome back to Agate Fossil Beds National Monument on International Day of Women and Girls in Science. We just heard from Daniela Balasha and her research on the camel Oxydactylus. Next, Kristin Watmore is here to share information about a little camel we're very familiar with here at Agate. It's the Stenomylus. This little guy behind me is the Stenomylus hitchcocki. With his 4 long, lanky legs, long neck, and oval-shaped head. Again, please start writing your questions and comments in the chat now. Go ahead, Kristin.
A woman wears a large straw hat and shows us a fossil fragment in one of her hands. Title, Kristin Watmore, Agate Fossil Beds National Women in Science Day, February 11th, 2024. Kristin speaks from a small corner of each screen. She's a white woman with long, light brown hair, pulled back with a headband. Then, 4 photos show Kristin holding a fossil, standing by a large research poster, sitting outside with her arm inside a hollow area of a cliff, and standing with other people indoors.
Hi, everyone. My name is Kristin Watmore. I'm a grad student at Cal Poly Pomona in Southern California, and I'm studying vertebrate paleontology. Thank you to Agate Fossil Beds for having me speak today. So just for a little bit of background about myself and how I got here. So I was like a lot of kids, and paleontologist was the first job that I ever wanted. And I had always been really interested in the natural and earth sciences. But for a while, I didn't quite know that paleontology was really a real job that I could actually have. So with that, I did my undergrad in biology, and it wasn't until my junior year of my biology degree that I met my current advisor, Dr. Donald Prothero. And he basically showed me that paleontology, it's a career that is possible. And he took me on as a research student and has showed me the wonders of the field since. And so some of these images here show you what I've gotten to do over the past couple years of getting into research. I've gotten to collect data from a bunch of different museum collections. I presented my research at conferences, and I've gotten a chance to do field work as well. And then the image on the very far right is me with my advisor, Dr. Prothero, as well as a couple of my research peers. I have a few more of them that aren't pictured as well. And it's interesting. It's been a really great experience having most of my research peers be other females that are really supportive of each other. And it's just been a true gift to learn and work alongside of them.
3 lanky deer-like animals stand in front of a pink background, titled The Stenomylus Camels. Research presented by Kristin Watmore in collaboration with Dr. Donald Prothero.
So with that, I'm going to tell you now about some of the research I've been doing in paleo. And so the group that I'm going to be talking about today that I've been studying are called the Stenomylus camels. So this is going to be presenting research that I'm currently working on in collaboration with my research advisor, Dr. Donald Prothero.
8 illustrations of different camels, some with back humps and some without, line up under a reverse image of the 7 continents, with the Americas on the right and Africa and Europe on the left. Symbols show where each species started. An arrow originates in North America and expands out to the other continents.
So it's understandable if when you saw the picture on the last slide that those did not align with the first thing that came to mind when you thought of a camel. The camels that we're familiar with today are like the Bactrian and the dromedary from the Middle East and Africa are large animals, and they have humps. There's also other camelids that are living today in South America, like guanacos, vicuñas, llamas, and alpacas, and those are all within the group of camelids. But millions of years ago, camels actually evolved in North America, and then they diversified there and over time migrated into these other places, and we're only left with the skeletal remnants of the presence of these camels in North America.
Geologic timescale from Eocene to Pleistocene that lists vertically. A single line follows the scale with the names of various camels listed as leaves off the main line. Stenomylus is the 6th leaf from the bottom between the Oligocene and Miocene. Then, silhouette of a camel with 2 humps and long droopy neck appears and quickly gets crossed out.
So today I'm just going to be talking about one of these groups of ancient camelids, which I'll box here. They are called the Stenomylines. And as you can see, they appear relatively early on in the camelid ancestry, appearing in the Oligocene and spanning all the way through the Middle Miocene. And you can also note from this tree here that there's a lot of morphological differences, variability seen in early camelids that really doesn't look like the camels that we think of today. And even more interestingly, we always think of camels having humps, but the majority of camelids living today actually don't have humps. So we don't assume that the camel group that I'm talking about today or other similar early camelids had humps either. So we're picturing quite different type of animal.
Kristin reads from a list of 4 bullet points under the title, What is a Stenomylene?
So what is a stenomylene then? So we usually call stenomylenes the gazelle-like camels, and this isn't because they're related to gazelles in any way. It's just the closest kind of description we can give based on their morphology. It's because they were pretty lightly built animals with long, skinny legs. And then they're also this group is known for their evolution of extreme hypsodonty. And hypsodonty refers to high crown teeth. So this is something that I've done research on in the past, and I presented on this last year. It's an interesting part of their evolutionary history. And so, like I mentioned, they are a North American group spanning the Oligocene through the Miocene. And then today, I'm also going to get more specific and look at 4 genera within the tribe Stenomylinae, which is within the overarching group of the Stenomylenes. And there's 4 genera in that group, Stenomylus, which we'll be talking about specifically today, but there's also Blicomylus, Racomylus, and Wyomylus.
Geologic timescale of the Cenozoic from 66 million years ago to the 1950s displays horizontally. A box highlights the mid-Oligocene to the mid-Miocene. 3 photos also display on the screen, each showing a lanky deer-like animal with very narrow body features. Kristin crouches next to one displayed skeleton where her head is taller than the animal's back.
And then just to give you a little more visual representation of this group, these are examples of stenomylenes in skeletal mounts in museums, and then reconstructions of what they might have looked like in life, as well as down on the bottom right is me for scale measuring the limb bones of a Stenomylus. And it just shows you how they're kind of like large dog size. They were not large animals like we think of camels today.
Kristin stands next to a research poster indoors with a name badge hung around her neck. Poster titled, Dietary Modifications of Teeth in Early Miocene Stenomylene Camels. She reads from a list of 3 bullet points titled, Conclusions.
So then briefly, just before I get into the new research that I'm working on, in case you watched my presentation last year for Agate, I talked about a project I was working on with a few of the genera in the Stenomylenes in terms of their hypsodonty, or how high crown their teeth were. And now this work has been published as well as presented at GSA and SVP. So some of the conclusions that I ended up making for this research was that the Stenomylenes do appear to be one of the most hypsodont mammals of their time, which is striking because it means they were more hypsodont than the horses that they lived alongside, like Meryhippus. And then genera like Blicomylus were particularly more hypsodont, and they were potentially specialists in arid environments with really gritty vegetation.
A group of Stenomylus skeletons displayed indoors in various positions, including lying on the ground. Text, list of described species, S. crassipes, S. gracilis, S. hitchcocki, S. culianensis, S. taylori, and S. tubatumensis. Then, black ink writing appears on 4 jawbones with long tubular embedded teeth. Kristin reads from a list of 8 bullet points. Finally, Kristin reads from a list of 3 bullet points titled, The Taxonomic Problem. Then she reads 2 main questions on the screen.
So now switching gears a little bit from my old project, now I'm going to be talking about my current research project I'm working on, which is about Stenomylus systematics. So now we're zooming in on just one genus within the Stenomylenes, which is the namesake genus Stenomylus. And the goal of this research is I'm looking to evaluate the validity of the taxonomy that exists for this genus. And there's currently 6 described species. And I'm going to be focusing on 2 of them, Gracilis and Hitchcocki, which I'll go into more depth on future slides. So what does the literature say about the Stenomylus systematics? So S. gracilis, so Stenomylus gracilis, is the type species for the genus, and is found in the lower Harrison beds. And some of the defining characters of this species in particular are said to be its larger size, smaller premolars, and taller molars compared to the other species in the group. Then there's S. hitchcocki, which is found in the Stenomylus quarry near Agate. So then if you're comparing the two, S. gracilis actually just comes from one layer below Agate quarry, the beds that the S. hitchcocki were actually found in. And then also I'll mention another one of them, because I have an image for it, S. culianensis, which is defined on a single specimen with a larger canine. So you can just kind of see all of them look similar at first glance, but that's why we have to do systematics to kind of see, are they actually different or are they the same? So what's the taxonomic problem here that I am actually trying to investigate? So this is actually quite a common issue in paleontology. So it's not unique to the Stenomylines, but this is a good example of a group to do this kind of research on. So the issue is oversplitting of this genus into more species than were likely to be biologically represented in nature. So previous studies had not really done statistical analyses to actually support whether one species was different from another species. Also, it's notable that some species are based on a single specimen, which is not typically the most robust way to do systematics today. And then also large samples of various Stenomylus species are found from the same locality. So we have to keep these things in mind when we're saying one thing is different than the other, especially if they were living in the same place at the same time and are not abundantly different from each other. My main questions for this research are: one, does the data support S. gracilis and S. hitchcocki as being distinct species? And then two, since variability is a natural part of living populations, as the taxonomy stands now, is this variability accounted for in the species designations that have been given? And this is important to think about the idea of interspecific variation, meaning variation within one species. Because this is quite a common phenomenon with things like sexual dimorphism, which will make a female and a male different from each other. It might be obvious or it might be more subtle, but these differences should be accounted for. And then also just naturally, some individuals are smaller or larger than others. This wouldn't by itself mean that we separate them into different species.
Kristin reads from a list of 5 bullet points titled Methods. 3 jawbones with long tubular embedded teeth have black ink written on them. Caption: Holotype of S. gracilis refers to the jaw which is a short length and curved similar to a boomerang. Caption: Specimen of S. hitchcocki refers to the jaw which is a long length and curves only slightly at its back end.
The methods that we're using to conduct this research include a standardized way of measuring kind of a proxy for size amongst these species. So we measure the premolar and molar tooth row lengths in both the upper and the lowers. And then we're also measuring the canine width and height for purposes of sexual dimorphism. We're also noting any consistent morphological differences that we see between species or that's been referenced in the literature for us to look out for. And then we're cross-referencing what we see with that literature. And then I also want to mention that this kind of statistical analysis typically involves looking at a species that has a good sample size to look at. So in this case, S. gracilis and S. hitchcocki do provide a large enough sample size to do these kind of statistics.
Scatterplot graph with P2 through P4 across the bottom and M1 through M3 along the side. Different color dots indicate S. gracilis or hitchcocki. Green, symbolizing hitchcocki, is the most abundant and is spread all over the graph.
So these next few slides are going to be showing you similar plots. Just to orient you, the x-axis is going to be the premolar row length and the y-axis is the molar row length. And then each color is identifying a different species that we've taken these measurements of and then plotting them together. So on this plot, this is showing this plot of the upper tooth row lengths. And what we can see from this, just visually looking at it, is that there don't really seem to be any visual clusters. If there's really a clear cluster, that would be supportive of the idea that, oh, this species is different than another species because they're not clustering together in size categories. And then we can run statistical tests on it that I won't go too deeply into, but the idea is that we can get values that show us if there is a significant difference between one species and another species. And then we can do further tests to see which group that is in. And so from this, we're actually getting a p-value that's showing us that there doesn't look to be a significant difference between species, which is supportive of the idea that maybe S. hitchcocki and S. gracilis should not have been split into separate groups.
Scatterplot graph with P2 through P4 across the bottom and M1 through M3 along the side. An additional species of S. kilianensis is added to the graph with only one plot point. Of 20 plots, 11 are in the middle cluster of the graph.
And so this plot is showing similar measurements plotted together, but these are from the lower tooth row. And in this case, we are getting a significant p-value, which means there could be a group in here that is significantly different than another species. We already know that there is one species that is pretty confidently different, an earlier species than the others. So it's likely that we're getting this signal from that. But a further test could confirm if this difference is significant between S. hitchcocki and S. gracilis, or if it's not.
Two scatterplot graphs with same structure as before. Left graph caption, premolar versus molar upper tooth row lengths. Manova test, p-value equals 39 hundredths. Right graph caption, premolar versus molar lower tooth row lengths. Manova test, p-value equals 82 10,000ths.
And these plots are showing basically the same thing that we saw in the last two. I just incorporated measurements that we took from museum specimen that were not identified to species level. They were just labeled as Stenomylus. And then that just helps add to having a larger sample size to do these statistics on.
Scatterplot graph with canine width across bottom and canine height alongside, with 13 plot points of 4 different species, 6 cluster in the top right corner and 3 cluster in the bottom right corner. Kristin reads from a list of 4 bullet points labeled Next Steps.
So as it looks preliminarily, it appears that Stenomylus hitchcocki and Stenomylus gracilis may not actually be different species. We'll have to do more stats on this to confirm this, as well as next step of increasing our sample size to do this research. But that's how currently it is looking for these two species. And then we also want to address the potential sexual dimorphism in the canine tooth, which is a part of that interspecific variation that I mentioned earlier. Here's just a simple plot showing canine measurements, and we can just kind of see that for each species, there does seem to be a smaller group cluster and then a larger group cluster. So like I said, we want to also perform more stat tests to just decide which species actually are different from one another. And then we will retain, at the end of this, we'll retain the valid species and then have to synonymize the species that don't have support.
2 photos next to a list of 2 implications. First, a small museum sign labeled Stenomylus hitchcocki, and second, a page from a book labeled Stenomylus. Highlighted yellow are the 4 species, hitchcocki, crassipes, kilianensis, gracilis.
So finally, it's important for me to finish with the implications that this kind of research can have for paleontology. So if we conclude that there is no evidence to support a difference between the Stenomylus gracilis and Stenomylus hitchcocki species, then Stenomylus hitchcocki is no longer going to be a valid species, and that name will have to be synonymized into S. gracilis. And this occurs because the rules of nomenclature, S. gracilis got the name first. It was the first named species in 1906. So it has seniority over that second name, S. hitchcocki, from 1910. So if there really is no difference, Stenomylus hitchcocki is going to disappear, and we would be left with gracilis as well as the other species, given that they have support as well. So this means that textbooks, museums, paleoart labels, they would all need to be changed because Stenomylus hitchcocki is actually the same thing as Stenomylus gracilis, if this is what our findings support. And this is just all connected to the idea that taxonomy is data in paleontology, and we need to have well-supported taxonomy to give us an accurate indication of what species diversity was in the past.
Stock image of a thick, short-haired camel with a droopy neck. A piece of grass sticks out of its narrow snout and mouth, which stares at us.
And so with that, I want to thank you all for listening today, and thank Agate Fossil Beds for having me. It's always great to be able to share my experience in paleo with other people, as well as what research I'm working on. So I hope you learned something, and happy National Women in Science Day.
I'm standing in front of the Stenomylus hitchcocki. Did you hear that, Kristin? Hitchcocki? All right, it's break time. When we come back at the top of the hour, we'll hear from Madison and her research on the tiniest deer you'll ever see. See you then.